When we introduce caches, we define a hit as when the data that the processor is seeking is in the cache, and a miss when it's not in the cache. And we mention hit ratio, that is the total number of hits divided by the total number of access, and miss ratio, that's 1 minus the hit ratio, or the total number of misses divided by the total number of accesses. In this lecture, we're gonna go and examine more closely the issues related with cache performance. We start with the measurement of cache performance, and for that we need to consider what are the components of the CPU execution time. The CPU execution time is formed by the program execution cycles, which includes the cache hit time, because in the case of a hit in the highest level of cache, in the L1 data or instruction cache, we are able to provide the data to the processor in a single cycle. So the time to access the cache in the case of a hit is already included in the time needed to fetch the instruction or to fetch the data. But then we have memory stall cycles. Those are cycles in which the processor cannot proceed because it's waiting for cache misses. Because when there is a cache miss, there is a penalty that is a certain amount of time that you have to wait until the data is brought from the lower level in the memory. So using some simplifying assumptions, we can say that the total time to execute in the CPU is equal the number of cycles that you need to execute in the CPU plus the number of cycles in which you stall, in which you are waiting for memory, times the clock cycle time. Well, the number of times that we stall will be the number of memory accesses that you have in the program times the miss rate, because that is the number of times that you try to do an access and you don't find in the cache, times the miss penalty, which is the amount of time that you have to wait every time that you have a miss. So we can now replace the miss rate with the number of misses divided by the number of memory accesses. And as you can see now, we have the number of memory accesses on the top and on the bottom. So we can simplify and we can say that the number of memory stall cycles is equal to the number of misses in the program times the miss penalty. That is the amount of time that you have to wait when you try to fetch a data from the cache and the data is not in the cache. So let's look at memory accesses now. There are two sources of memory accesses in the program, and this is very important to remember. There is instruction fetching. So every time that you execute an instruction, you must access the memory. In this case, most of the time will be the cache. To fetch the instructions. And then you have data load and store instructions. When you have a load or a store instruction, you have one additional memory access for those instructions, that is the memory access to fetch the data. So even instructions that do not access data, that are not loads and stores, they do one memory access, that's to fetch the instruction itself. And once you fetch the instruction itself, if the instruction is either a load or a store, there is a second access that is to access the data or to write into the cache. If I have a unified cache, then the data and the instruction are in the same cache. And that is common for the lower levels of cache, L2, L3, etc. If I have a split cache, I can have different miss rates for the data cache and for the instruction cache. And the split cache it happens in pretty much all architectures only at the highest level in the cache. So how do I calculate cache performance? And for that, we're going to do an example in here. We're going to assume in this example that the miss rate of an instruction cache is 2%, and that the miss rate of a data cache is 4%. And we'll assume that the CPI, that's the average number of clocks per instruction in this processor, is 2 if I have no memory stalls. So if I would have perfect cache that always hit in all instruction accesses and in all data accesses, the average number of clock cycles per instruction will be 2 clock cycles per instructions. And the miss penalty is 100 cycles for all miss. So it doesn't matter whether I miss in the data cache or whether I miss in the instruction cache, I have to pay a penalty of 100 cycles every time that I miss. The question that we need to solve is how much faster a processor would run if it had a perfect cache that never miss. So we have a real cache. In our real cache, in the instruction cache, I have a 2% ratio of miss and a 4% ratio of miss in the data cache. And we're going to assume that the frequency of all loads and stores is 36%. What that means is that 36% of the instructions will be loads and stores. And remember, those instructions are the only ones that we're going to access the data cache. So for every instruction, I have an access in the instruction cache because I have to fetch the instruction. 36% of the time, or for 36% of the instructions, I also have an access in the data cache. So I have my processor, I have the memory, and I have my instruction cache. So, and I like to solve those problems, this type of problem, by using this type of diagram that we are showing in this slide, because it's much easier to visualize what's happening. I could solve the entire problem just writing equations, but I may make some mistake when substituting the numbers in the equations. It's easier to see what's going on if I do this kind of block drawing. And this kind of block drawing I created a few years ago when I noticed that students were having lots of problems and making lots of confusion when they are only writing equations. So I have the processor, I have the instruction cache, I have the data cache, and I have the memory. And one way, an easy way to solve this problem is to assume that I have a certain number of instructions. The problem statement does not tell me how many instructions a program will execute, but I can just assume. And then if I'm going to use that number consistently, and that number will be simplified and will disappear from my results. So let's assume that I have a processor that executes 1,000 instructions. I could assume any number. I could say n instructions, but I find that it's easier for students to reason about this if I have a real number there. So let's say that I have 1,000. And the problem says that I should assume that the frequency of all loads and stores is 36%. So if I have 36% frequency of loads and store, it means that there will be 360 references to the data cache. Because I'm executing 1,000 instructions, 360 of them will access the data cache. And the problem also tells me that the processor has a CPI of 2 without any memory stalls. So what we need to keep in mind is that the instruction fetch is fetching from the instruction cache, and the memory stage of the pipeline is executing from the data cache. So these two accesses are happening at the same time. Therefore, if I don't have memory stalls, I have 2,000 cycles for the execution of the code. And I know that the miss rate of an instruction cache is 2%. So of the 1,000 instructions that come into the instruction cache, 20 of them will have to access memory. And I know that the miss rate of the data cache is 4%. So of the 360 references that I have into the data cache, 0.04 times that will be the number of requests. The number of requests will be 14.4. Don't worry for the fact that I did not get an integer there. If I had 10,000 instructions, that number would be 144. Remember, the number 1,000 instructions was arbitrary. So it's okay for me to have a fraction at that point. So I got 14.4 requests into the memory from there. And then it says that the miss penalty is 100 cycles for all misses. So in the memory, I get 100 cycles delay when I access the memory. So now I can compute the stall cycles. The stall cycles will be 34.4 times 100. That's 3,440 cycles that are my stall cycles for this machine. What I want to know is how much faster a processor would run with a perfect cache that never missed. So with a perfect cache that never missed, I would have 2,000 cycles for the execution of the code. So the real execution is those 2,000 cycles plus the 3,440 cycles that I had to wait for the memory. So if I divided that sum by 2,000, I get 2.72, and that is the difference between the real and the ideal. So now I can compute the amount of time that I spent on memory stalls, and I will take the time for memory stalls divided by the total time, and I can see that 63% of the time the processor is not doing anything, it's just waiting for memory. And then there is an interesting question. What happens if the CPU is made faster without changing the memory speed? So let's say that the CPU now if the ideal CPI is 1 instead of 2, so I change the design of the processor, I managed to make the processor much faster, so it has a lower number of clocks per instruction. And this question is here to illustrate what has happened historically with the evolution of processors, that the processors got faster and better, but the memory did not get as faster or didn't improve at the same rate as the processor did. So what happens in that case? So in that case, I'm going to just fix my equations here in this slide. So instead of 2,000 cycles, now I have 1,000 cycles without stalls. So if I replace that 2,000 by 1,000 in this equation, now I get 4.4 is the speed up that I will have with the ideal divided by the real one. And now if I want to know the amount of time that I have spent on stalls, I have to divide the number of stall cycles has not changed because the memory has not changed. The only thing that changed was the processor. And now I see that the processor will be spending 77.4% of its time doing absolutely nothing, just waiting for the memory. And the reality of most modern processors is that they spend the majority of their time waiting for memory. So whenever we do projections of how much faster a computation will be if I execute in multiple processors, I have to take into the consideration that that single processor may have been waiting for memory for many applications. So when I increase the number of processors, the speed up that I may have may not be different, may not be proportional to the number of processors that I add to the system.